My name is Lauren Cassidy, and today's data set is organized in the table here. And we are going to be to determine the recombinant class, which is when the offspring inherits a combination of alleles that is different from the parents. And it could be determined by the um, genotypes that produce the lowest number of frequency of offspring. So here, the first two would be considered the parental classes. Therefore, the rest of these would be considered the recombinant class, which means there is one crossover that occurs during meiosis versus the double recombinant class, um, which is when there's a double crossover that occurs during meiosis, and it could be determined when by the lowest number a of offspring produced. So here it would be the A plus plus would be considered the double recombinant class. And we could use all of the information to calculate the map distance between the genes, which is the number of recombinants divided by the total offspring times 100, and we calculate that between each gene. So here for A and B, we the recombinants, and then we add up the total number of offspring from table for each recombinant class, and we then add that and divide that by the total number of offspring, which is 5,742, which is all of these added up. And is that produces 28.7 centimorgans, which is the unit of measurement for gene distance. And we do the same thing for the distance between B and C genes. And that produces a distance of 27.3 centimorgans. And again, for the distance between A and C genes, so the recombinants, and we add the total number for each one divided by the total number of offspring, and that produces a distance of 28.4 centimorgans. So for the final gene map here, we could see each of the distance between that, and we can use that, and it produces the final gene map where A is 28.4 centimorgans away from C, which is 27.3 centimorgans away from B. And then A to B is 28.7 centimorgans. We could also use the information provided in our data set to calculate the coefficient of coincidence and interference. So first we would have to calculate the expected double crossover, which is the distance from B to A times A to C, divided by 100 times the total number of offspring. So for expected, we have our 27.4 times 28.4 times 27.3, which was found previously. And we divide that by 100, and that produces a total of 445. And then we have our observed of 240. And to calculate our coefficient of coincidence, it's observed divided by expected, and that produces 0.539, and then our interference is 1 minus the coefficient, and that's 0.461, and this um means that the observed frequency of the double crossover between the two gene loci is 53.9% of what would be expected if the crossovers occurred independently of each locus, suggesting a moderate level of interference where one crossover reduces the likelihood of another nearby.